Hi, my name is Ben Guan, and today I will talk to you about my 447 final project and how I go from start to finish. And first, we use the Hamiltonian calculation, and then we find the physical parameters using the concept of system identification. The next step would be using a multiple control and doing a state design. And in this case, we have four states in total. And the next step would be doing the swing up control, which involved uh, finding the controller, and the very last step would be balancing the second joint of the stick, and which we use linear Jacobian linearization and pole placement. So the way Hamiltonian works is that it calculates the total energy of the system, and based on how the mass is being distributed, it calculates the energy that distributed to the individual joints. And the next step of the derivation is that we transform the variables from the mechanical world to the electrical world. In other words, we relate the force or torque to the voltage of the motor. And note that we are using an array to store the Hamiltonian of 10,000 data points. So the way that we acquire the data point is that we have two sinusoid going into the voltage of the robot, and we set the step size to 0.001 and run the program for about 10 seconds, and we acquire 10,000 data points from there. Um, and as we know, the mechanical energy is equals to the integral of the torque over the distance. The input energy of the motor is equal to the sum of the required energy and the energy loss. Therefore, the H matrix is the energy required, and F matrix is the energy loss due to the friction. And combining the H and the F matrix, we obtain the A matrix. Taking the inverse of the A matrix and multiply that by the D matrix, we obtain all the theta values. And I will explain what thetas are later in this presentation. So we ran the Hamiltonian MATLAB file and we found the thetas. And the thetas are unique to each robot, and it depends on how the joint and the gear ratios are in the robot, and depends on the dynamic and or static friction in between joints. And theta 1 is related to the inertia of the first link. Theta 2 relates to the inertia of the second link, which is a cylinder. And theta 3 relates to the inertia of the link 1 and link 2. Theta 4 relates to the gravity. Theta 5 and theta 6 relates to the friction of link 1 and link 2. As I said, thetas obtained from different stations depends on the physical characteristic of the robot, because of the inertia and friction of each link in each robot is slightly different, and it will eventually determine how much energy is being distributed to each joint. So as you can see, we first built a selector which controls the state of the robot, and one being at the very bottom, and three being at the top, and two being anywhere in the middle. And as you can see from at the bottom, we have a state diagram, and it goes from state 1 to state 3, and then to state 2, and then back to state 1. So the order of the state diagram will be 1, 3, 2, 1. Please note that we add in a fourth state to compensate the robot and allows the robot to readjust itself when interrupted. So the selector takes in two inputs. It takes in the previous state and the position of the second link, and then output the current state. And you can see we use a memory block there to store the previous state. So as you can see from the block diagram, we subtracted the actual position of link 2 from the desired position and use that as a feedback. And note that Q2 is being normalized using arctan2 functions in MATLAB. Next step of the process, we built a swing up function which provides voltage to the robot and allows the robot to go from state 1 to state 3. It involves the feedback loop, And the requirement in this project is that we can have a 5% overshoot and a 0.15 seconds of peak time. And using those parameters, we calculate the feedback gains, and we got Kp equals 12.3 and Kv equals to 0.00084. So the second component is the balance control. We wrote a MATLAB function that calculates the Jacobian of the systems, and as you can see, the Jacobian linearization is that we express x dot in terms of x and the input. So we have x dot equals ax plus bu, and so f1 is just q1 dot, f3 is just q2 dot, and f2 and f4 are in terms of q1 dot and q2 dot, and we calculate partial derivative of f1, f2, f3, f4 with respect to q1, q1 double dot, q1 dot, q2, and q2 dot. And then using the A and B matrix, we first set the desired position to 0, 0, 0, 0, because that's what we want the robot to be. And then we run the function to get the k values, and k is a 4x1 matrix. Note that we use a pole placement technique to calculate the k values, and in MATLAB we use a place function, and we place the poles in minus 5.1, minus 5.2, minus 5.3, and minus 5.4, and then we calculated the k values from that. And as you can see on the right, if we run the program in Simulink, and the second drone actually balances. Other method that we can use in this lab is that we can use a PID controller to swing the first link and balance the second link. Another thing that we can do is to reduce the step size of the program when we do the Hamiltonian calculation, or run the program for a bit longer to get more data point. That way we can get a more accurate value of the thetas, which relates to the characteristic of the robot. And that's all I have for the presentation part, and below I will show you different modes of the robot.
Somebody you done slept with. Hold up, that's my Nina Cherry shit. I got something slicker. Let me just sip up on this liquor. All I wanna do is smoke a little chronic, slam you like Onyx, and get you hooked on this Biggie Smalls phonics. 102, how to squeeze 22s in them Reebok shoes. Hey!